Okay, we need to finish up section 2 then. I didn't end up giving you guys any homework last time since we didn't get as far as I kind of was thinking we might. So I want to finish up section 2. I want to do all of section 3 today. Hopefully we can get started a little bit on section 4. And then on Tuesday, we would be able to finish up section 4 and do section 5 on Tuesday, and then do a little bit of reviewing. And the next test comes back around again next Thursday is the current plan. Chapter 6 is setting a lot of the foundation for what we're going to do with things in Chapter 7 and 8. We're really looking at what the z-score stands for and how we can convert things into that normal or the standard normal distribution so that we can use it to figure out how often things happen and whether or not things are normal or not normal as we do things. So last time we were looking at using the standard normal distribution. Remember, the standard normal distribution has a mean of 0, a standard deviation of 1. And it has that nice bell-shaped curve when we do things. When we were using our tables, I want you guys to go ahead and use the tables and find the probability that you get a z-score that is between negative 1.34 and 2.17. Being able to read these tables are going to be helpful. I'm going to be showing you some of the calculator shortcuts on doing these. But as we go along, being able to read these tables are going to be really helpful and important things to be able to do. Remember that when you read those tables, it always gives you your area to the left, so the probability that it's less than each of these values. So this is the z-score for that. That is the z-score for that. Or sorry, this is the area to the left of that z-score. This is the area to the left of this z-score. So if I'm wanting to find the probability that it's between these two values, because this is not your z-scores, those are your areas. Looks good, Jacob? I know you found it from the right spot, or I guess you're right from that spot. But now, if I'm wanting the probability that it's between those, this is the area to the left of this one. This is the area to the left of that. If I want to find the area between, what would I do with those two? Yeah. Where did you get that? You drop down a line, go back up to the blue line. Wait, it was 1 point, or 2.1. We're doing 2.1 that way. You went up 1. It's like I knew something, and I kept looking at your numbers now. So make sure you follow the right line. You've got the right idea, though. Okay, so your probability that we're looking for the area between these two things, we've got that negative 1.34 is somewhere around in here. The 2.17 is somewhere around in here, and I'm wanting the area that it's between these. So that was when we subtracted. The area to the left of the 2.17 was the 0.9850. The area to the left of the negative 1.34 was 0.0901, and so you wanted to subtract those. And as you subtracted those, everybody was getting that area of 0.8949. So being able to read your information from the tables and figure out what we have. And again, this is important that we remember this is when we have the standard normal, that the mean is 0, and each of these standard deviations, it's one standard deviation in each direction. We're going to be having to convert things to standard normal in this next section, in section 3 today. Now, looking at how the calculator can do it. If I wanted to find the probability that my z-score is between 1.2 and 1.7, and those are the ones that we did last time, and that's where we got the 0.0705 was in your notes last time. So I know this is what my final area is going to be. To find that, the calculator can do it. One limitation the calculator has is it only finds the area between two things. So when you're looking for having just the area less than or the area greater than, we have to get a little more creative. But to put it into things, you're going to go into second and vars, so that distribution that we had before. And now what you're wanting to do is that normal CDF, which is just that second one down, which is giving me the normal distribution, and it's a cumulative distribution, so it's cumulative from the left is what that's telling you we're doing. And what you're going to put in is your left z-score followed by your right z-score. So in this case, we'll put the 1.2, comma, the 1.7. And that gives us that same 0.0705 that we did last time. So you're doing your second vars to get your distribution, and we're doing the normal cumulative distribution. Okay, so I want you guys to go ahead and do it for the one we just did. So we just did it with that negative 1.34 and the 2.17. So you put in your leftmost, and then you put in your rightmost. And you should be getting the same answer that we had before of the 0.8949. We round that up to 4 decimals. Now, as I mentioned, we have to get creative when we don't have something between. Because if I have it as the limit as figuring out the left z-score followed by the right z-score, that's great, until I'm wanting to have the area that's just less than 1.98. Well, when we have a z-score, can z-scores be negative? Yeah, and there's not an end to how negative things can get. And so what you have to do, because I just want to know it's everything from the left forever until 1.98, you have to pick a really small value for your leftmost. And so when you go to put this one into your calculator, you're going to do things like your normal CDF. And you have to put in a very, very, very far to the left number. And so pick something like negative 9,999. And then pick your end point for the right is that 1.98. Because the probability that we're going to get a z-score that's at negative 9,000 is basically nothing. And so it's not going to affect us as we go through doing that. And so if you put that one in there, if you compare that to what you have on your tables, if we look at what our table tells us for the 1.98, and again, it's the table's telling me what's less than also. But if we go to the 1.98, we end up with the 0.9761. So if you're doing the 1.98, so you're going to 1.9 along the side, the 0.08 from the top, and getting that 0.9761. Well, when we did this with our calculator, it also rounds to 0.9761. So you're going to get the same answer. The calculator carries those extra digits on there, so it doesn't have the same rounding as we have before. So being that this is 0.97618, that's really close to where it would round up to that next thing. So it's going to have, if you're looking for the area between things, there's going to be several times that your answer in the back of the book will have both, with technology and with the tables. Because if you were finding the area between two things and you're using the calculator to do it, because it carries those extra decimals, it may round a little bit differently than what you'll get when you're doing it by hand with the tables. And so both answers will be on there. Questions there? Now, all of those have been where I'm giving you the z-score and I'm asking you to find the area. What if I wanted to go backwards? What if I knew what area I wanted and I need to know what z-score is going to give me those values? Well, if I'm going backwards, the first thing you want to do is to give yourself a bell-shaped curve. I don't expect it to be like an awesome bell-shaped curve. You've noticed how I draw things. It's not great. But just give just a general bell-shaped curve and mark in there where your things should be. If you're looking at an positive z-score, it should be to the right of the mean. If you're looking at a negative z-score, it should be on the left side of the mean. And just shade in that area that you're looking for. So if I give you the z-scores and I want to find the area between two things, we'll put both of those endpoints and shade that we want the stuff between. If I want to know the area to the right of something, then shade that area to the right of it. What we have to remember is the tables will always give us the area to the left. The calculator is always calculating the things that is the area to the left. So we have to be able to shade what we're looking for and then figure out how to work with it from the left side when we're doing stuff. Now, using the cumulative area from the left, so we've shaded what we're looking for on the right, and now we're going to say, what are we looking for on that left side? I'm using the cumulative area from the left. Locate the closest probability in the let me start over because I just realized I changed in the midstream from knowing the area to knowing the z-score. So first half, when we're looking at this, if you know what area you want, draw yourself a nice little curve. If you're wanting an area that is greater than, you're going to have to change that to an area that's less than. So if I wanted the top 5%, and I wanted to know what z-score is going to give me just the top 5%, well, if I'm looking at the top 5% would be up about here. Well, that means my area is the left. That is an area from the left. Once we know the area to the left, what we're looking for, locate the closest probability in the body of the table and identify as being 95%. I'm going to look at my table for 0.95. And that'd be the same as the 0.9500 is what you're looking for. And just figure out what the z-score is that's going to be the closest to that. Questions so far? And there will definitely be some rounding on these because these aren't always going to come out to be nice and perfect. So if I look at some examples, this is the exact same one I was just saying. If I want to find the 95th percentile, so you're trying to figure out what would cut off the top 5% from the lower 95%. So that's the same as finding the 95th percentile. So finding out what is going to give me an area to the left that is 95% of those values. And then to find that z-score that goes with it. Looking in your table, will I be looking at the positive or the negative side for your z-scores? Just from the picture, does it look like it's on the positive or the negative side? It's on the positive side. If my area is bigger than 50%, the 50% is smack dab in the middle. 50% is on the left, 50% is on the right if it's a perfect normal distribution. And so as you're looking at this, if your probability is bigger than 50%, you're on the positive side. So look in your tables and find the 0.95 in the body of the table. So in other words, what you're looking for is now, instead of reading across the sides, what you're looking for is inside of here. Well, as I look inside of here for 0.95, I have 0.9495, I have 0.9505. Notice there's a little asterisk in the middle. That's because 0.95 gets used so much. There's a lot of us that cut off, we want the bottom 95%, the top 5%. We use that one so much. If you follow the little arrow, it tells me that getting an area to the left of 95% has a z-score of 1.645. So that one gets used a ton, and so that's one that's going to be actually a z-score that you're pretty much going to have memorized before we get too far, of being that 1.645. So that gives me my z-score as my cutoff of how many standard deviations above the mean we would be looking at to get that 95%, having 95% less than that value. Now, what if I wanted to just know, I want the cutting off the bottom 2.5% and the top 2.5%. So this time what I'm looking for is I want to have the majority, 95% of the values fall in here. What are those two extremes that would cut off that other 5%? Well, if I'm looking at figuring out what those z-scores are, since I'm wanting 5% to be in my two extremes, cutting that in half means 0.025 on the bottom half, 0.025 on this top little bit. So finding those two z-scores. Let's look at the positive one first. Actually, let's do the easy one. Let's do the negative one first. If I'm doing the negative one, what's the area to the left of this? 0.025. So we're on the negatives, so look at your negative one and find the area to the left of being 0.025. So looking in your body of your thing, you're looking for that 0.025. In this case, it's another one that comes out to be nice and exact. You can have exactly that 0.025 in here. Well, if I have that 0.025 and I read what that number is, over here on the left we have the negative 1.9. Across the top we get the 0.06, which means what is that number? Okay, negative 1.96. And so my negative z-score is this negative 1.96. If I'm trying to find my positive z-score, if it's going to have 0.025 as the area to the right, what's the area to the left of that? Everything under the curve has to add up to be 1. So if I already know what the stuff on the right is, to find the left, okay, 1 minus the 0.025 would be the 0.0975. How about I do that math right? 0.975? Is that right? No, 0.9975. Why? First time was right? All right. Yeah. So find what's your area to the right. So look for the 1.9 or look for the 0.975 and figure out what the z-score is. This time we'll be on the positive z-scores. And what are we getting? Good, 1.96. It's nice friendly symmetry within doing this. Your normal distribution is a standard normal distribution is a nice perfectly normal curve. And so everything is perfectly symmetrical on both sides. Your mean is 0 in the middle, your standard deviation is 1. So when you're looking for the areas in those extremes, you're going to have the same numbers on both ends if you have the same amounts on both sides of those. So it does have symmetry, so really I didn't have to find both of those. Now also notice that we talk about the fact that 95% of the values fall within 2 standard deviations of the mean. Your z-score, when we're looking at a standard normal distribution, your z-score is telling me how many standard deviations above and below the mean it is. So instead of being exactly 2 standard deviations, it's really 1.96 standard deviations above and below the mean is where 95% of the values are. It's pretty much 2 standard deviations above and below the mean. That's where that 2 standard deviations being my usual values. It ties right into the fact that this is a nice standard normal distribution. So if you have a normal distribution, things fall within 2 standard deviations. 95% of the values fall within 2 standard deviations. Looking at our critical value, the expression z sub alpha, so your z-score is what we're looking at, sub alpha. The alpha denotes the z-score with an area of alpha to its right. So when we looked at having that first one and we did the 5% to the right, that was that z sub 0.05 was the 1.645 that we just looked at 2 slides back. when you're figuring out the area as being area 5% to the right, so finding that bottom 95%, finding the 95th percentile. The 95th percentile is going to be where I have the z-score that has 5% to the right of it. So if I want to find z of 0.002, this is telling me my alpha is the 0.02. I think I said it wrong the first time. Alpha of 0.02, which means I have 2% on which side, the left or the right? On the right. So I'm wanting to figure out the 98th percentile. So I'm only wanting to have 2% as my area to the right. If I'm given the area, we need to figure out the cumulative area from the left to be able to read it from our tables. So if I want the top 2%, that means I'm also finding the bottom 98%. So when we take that 1 minus the 0.02, we're looking for the 0.98. So find the 0.98 in your table. Now, out of the ones we've done, everything else has come out really pretty friendly, and they show up pretty easy. This guy doesn't show up quite as easily. If you're looking for the 0.98 in your table, we've got 0.9798 and we got 0.9803. Obviously, 0.98 is somewhere between those two things. We're only going to estimate our z-scores to 2 decimals, and so we've got to figure out which one of those is closest. Which is closest to 0.98? Heard a little bit of both. Okay, let me ask this question. How close is 0.9803 to 0.98? Okay, it's off by 0.0003. How close is 0.9798? Okay, 0.0002, which is closer? Okay, the 1.0002 is up closer. So the 0.9798 is closer to 0.98 than what the 0.9803 is. So we would end up using this as the 2.05. And is everybody good reading that off there? So once you have that 0.9798, we're going to go to the 2.0, reading it from the left. My second decimal place is that 5. So 2.05 would be my z-score. I did say 2.05, didn't I? Okay. Questions? Let's look at number 50 on page 263. Okay, first of all, reading through the directions at the top on this one. We assume that the thermometer readings are normally distributed with a mean of 0 degrees Celsius and a standard deviation of 1.00 degrees Celsius. A thermometer is randomly selected and tested. In each case, draw a sketch and find the temperature reading corresponding to the given information. So we've got this where we're having the mean reading, because 0 degrees Celsius is the freezing point of water. And so you're reading the freezing point of water. The mean is 0, which is what it should be. But these guys are off. Some of the thermometers read a little hot. Some of the thermometers read a little cold. And so we're looking at they could be off with a standard deviation of 1 degrees either direction. And so on number 50, I want to find P sub 1, which is the first percentile. That is the temperature reading separating the bottom 1% from the top 99%. So we've got different ways that we can express this. If I'm saying P sub 1, that's reading that as a percentile. So this is saying I want the bottom 1% compared to the top 99%. So if this is the first percentile, and we looked at the percentiles in, I think that was chapter 3, I think is when we looked at the percentiles. And so when we want that first percentile, I'm actually looking for a z-score of what? What would be my alpha? If it's 1% to the left, that's what to the right? Okay, the 99%, so the 0.99 to the right. And I'm wanting to find that z-score that'll cut that off. Well, honestly, the p sub 1 is an easier way to read it because it's telling me my area to the left. If I'm wanting the first percentile, I am only wanting 1% as my area to the left. So I only want to have the 0.01 as my area to the left. Will that be a negative or a positive z-score? Okay, it's on the negative side because it's definitely smaller than 50%. So finding the area to the left of being the 1%. What are you guys coming up with? Okay, so that gives me what is my z-score? Okay, Hillary's going with negative 2.33. Anybody agree or disagree? If I'm looking for that 0.01, if we look at the 0.01, 0.01 is really close to 0.0099 and 0.0096. Closer, oh, how about that goes to the right side? 0.0099 or 0.0102. Only off by 1 10,000th versus 2 10,000ths. And so we're going to go with that 0.0099 as being the closest value. And so we're going to end up using the negative 2.3, and then our value appears the 3. So negative 2.33. Questions there? Okay, to use our calculators then. Our calculators can also find the z-scores that give us the area to the left. And these are always going to be the area to the left of those scores. So to find that, you're going to use the inverse normal. So you're going to still go into second and var, so you're still doing the distribution. And you're doing an inverse normal distribution. So inverse means you're undoing. So if you're undoing your normal distribution, that's why this is your inverse norm. And then you're going to put in your area to the left. So for that last one, if we want the area to the left to be 1% or 0.01, we'd get the negative 2.326. So if we were actually, because we knew it was somewhere between negative 2.32 and negative 2.33, this tells us better what those decimals are. But it was still rounded to 2 decimals is the negative 2.33. And our z-scores are just going to round to 2 decimals only because that's what the table does. If I wanted to find the z-score for the upper 2.5%, so if I wanted to cut off the z-score just for that top 2.5%, what am I going to put in for my calculator? Because and these, I highly recommend drawing yourselves a picture. Again, they don't have to be great. If I want the upper 2.5%, when I put this in, it's always the area to the left. The upper is to the right, so what am I going to put in my calculator? It's going to be an inverse norm because I'm trying to find the z-score that gives me this area. So I know the area. I'm trying to find the z-score. Okay, it's going to be the 0.975. Why? Good. So if you take the inverse norm of 0.975, is that the 1.96? what this is finding is the z for that 0.025 to the right is your 1.96. On this problem, since it's just asking what is the z-score, if you write that the z-score is 1.96, that's also the same thing. This just gives you a little bit more information, but yes, just putting z-score being 1.96 is good. Okay, other questions? So the tables and the calculator both are giving you your area to the left as you're doing these. I recommend you understand how to read the tables and you're capable of reading the tables. I'd also recommend knowing how to use your calculators to do these, because depending on the problem, both of those are going to be really useful. Especially as we go to this next section, in section 6.3, where we're going to be turning things into our standard normal distribution. Most things that we work with don't have a nice friendly mean of 0 and a standard deviation of 1. If I'm talking about figuring out stuff about the ages of our students, and I wanted to say what is 95% of the ages of students fall in what range, well, when we're looking at having ages of students, you don't have a mean of 0 and a standard deviation of 1 for the ages. We've got to convert it into a standard normal distribution just so that we can use this information. And that's what we're going to be looking at doing here, is doing that conversion. So this section presents methods for working with your normal distributions that are not standard. That is, the mean is not 0 or the standard deviation is not 1 or both. The key concept is that we can use a simple conversion that allows us to standardize any normal distribution. So we can change things into our standard normal distribution, and then we can go back to our tables. I don't want to have to create and have somebody create a new table every time you change the mean by just a little bit or the standard deviation by just a little bit and have to come up with a whole new table. It's much easier to take your information you have and convert it into your standard normal distribution so that you only have to have one table. This is just a fun little thing. Oops, missed it. Try that again. This is showing how, well, what this is showing is if you take people's names, so if I go with my name, and it shows the trends, and you can see that the name Tracy has a nice normal distribution. So the pink is the girls and the blue is the boys using the name Tracy. And you can see how it's kind of increased. It's got the peak that we have, and then it's decreased. It's pretty symmetrical. So unfortunately, these can kind of tell you sort of the age range of people, because you can look at, all right, their name was popular in this range, so this is probably somewhere around when they were born, when you're looking at those kind of things, and being able to see what kind of distribution we have. But it's got a mean. The mean is definitely not 0, and because it's talking about the years. The standard deviation is not 1. Not all names are going to have a nice normal distribution. If we go with my son's name, this one's bimodal. It's got 2 different times when it was pretty popular. So it does not have a nice normal distribution. You've got the older generation that used the name Samuel, and now you've got it coming back again of being more of a popular name. Actually in the process of falling off in popularity, but still a popular name. So we could look at, well, we could just have fun and look at everybody's names, since there's not that many of us. Oh, Jeremiah, you're looking like your name's on the rise. Yeah. Versus, I can spell. Oh, Kristen, your name's on the, yours is pretty symmetrical. I don't know that I've ever seen one that symmetrical. It definitely had a year that it was popular. Okay. Well, it looks, I don't know why, but it definitely puts a definite time when that was the most popular name. That's true. Aaron, again, yours is pretty symmetrical. This is crazy just how symmetrical some of you guys are. Tiandra, it's going to be interesting to see how yours comes out. Nope. You didn't come out, sorry. Larry, is yours very symmetrical? Yours didn't show up? All right, we put the Y on there, then you get to be more symmetrical. But you're still not a great normal distribution. Hillard. I've never heard the name Hillard. Even back in the 1900s, early 1900s. That's just not what I've seen before. All right, so again, things can have the nice normal distributions, but just because they have the nice normal distributions does not necessarily take them into being the standard normal distributions. So what we have to do is convert things over. We want to convert them into where they have a mean of 0 and a standard deviation of 1. And Aaron, if you'll grab the stuff off the PowerPoint, either the PowerPoint or off the Integrity video, so you can catch the homework. So this is how we're going to convert those. So when we do know the mean and the standard deviation of the population, then we can use this conversion to get our z-scores, where we're going to take the x value being the value that we have minus the mean divided by the standard deviation. So if I knew the mean of the name Tracy and the standard deviation for the name Tracy of what those values were, and I could take my birth year, I'm not telling, minus the actual mean of the values divided by the standard deviation, I can figure out how close to normal I was as far as was my name, was I named that during the time it was popular, or am I one of those extremes? So that's what you're looking at doing when you're taking these kind of things, but you're taking it and turning it into a standard normal distribution. This is something we're going to use a lot of. So this is definitely a formula we're going to use a lot, and I'm pretty sure that's a formula that's on your reference sheets. But I don't want to lie to you, so let me double check that. Yeah, that's on your reference sheets is one of them that we're going to be using, of converting things into your standard score. Now notice this is if I know the population mean and the population standard deviation. So what we're doing is converting your non-standard normal distribution when your mean is mu and your standard deviation is sigma. We're going to use that conversion of the z equaling x minus the mean over the standard deviation to be able to convert that into a standard normal distribution where we now have a mean of 0 and a standard deviation of 1. If you've had college algebra, that's one of your transformations. But you're just transforming that from one style and transforming it into another type of function. Questions so far? So, some hints to pay attention to before we start looking at those. One is don't confuse your z-scores and your areas. Remember, your z-scores are those distances along your horizontal scale. Those are telling you how many standard deviations away from the mean you are. Whereas your areas are the regions under the normal curve. So your area under the curve is telling you your probability. So table A2 lists your z-scores in the left column and across the top, and your areas are what we had in the body of the table. So paying attention to what you have, each piece of information you're using. Be careful with that. Another thing to pay attention to is to pay attention to whether you're using the left or the right side of the graph. Are you working with something that has is above the mean, or are you looking at something that's below the mean? Because that'll tell you if you're on the right side or the left side. If you know the areas, you're talking if you have an area that's more than 50% or an area that's less than 50%, tells you if you're on the left or the right sides. Also, your z-scores can be negative. So your z-scores will be negative if when it's in the left half of the normal distribution. So be careful of just paying attention to the fact that if you know you're looking at something on the left side, make sure your z-score is negative. On the other hand, areas will not ever be negative because you're dealing with a probability. The smallest area it can contain is 0, so you're not ever going to get a negative value. If it does not have any chance that it'll happen, then your area can be 0. Because your probability could be 0. Or very close to 0 sometimes. Questions on those? Okay, let's look through an example then. On page 273, if we look at number 26A, the Marine Corps height requirement for men. The U.S. Marine Corps requires that men have heights between 64 inches and 80 inches. Find the percentage of men who meet the height requirements are many men denied the opportunity to become a Marine because they do not satisfy this height requirement. So, if we're looking at what we have, I guess I need to find the mean first. Up at the top, it tells men's heights are normally distributed with a mean of 69 inches and a standard deviation of 2.8 inches. So the population mean is the 69 inches. Population standard deviation for men is the 2.8 inches. It's above the blue directions. It says up there in exercises 21 through 26 to use that. So when we look at this one, we're wanting a man between 64 inches and 80 inches. I want to find the probability that the men are going to have heights between the 64 inches and the 80 inches. Now, first of all, is the 64 inches above or below the mean? Below. So I expect to have a negative z-score for it. Is the 80 inches above or below the mean? So I expect to have a positive z-score for that. To find my z-scores, your z-score, you're going to take x minus the mean divided by the standard deviation. So for the first one, we're going to take the 64 minus the 69 divided by the 2.8. Should be getting negative 1.79. Now make sure you are making it do the order of operations correctly, that you're making it subtract before you divide. So either put the 64 minus 69 in parentheses divided by 2.8, or 64 minus 69 equals, and then divide it by 2.8. Because that's what my tables do. It's really not any better reason than that. It's just what the tables do. So now if we do it with the 80, so now my z-score would be the 80 minus the 69 divided by the 2.8. We should be getting 3.93. Is everybody okay with that so far? We haven't learned that yet. Now, what we're looking for, you're asking, yes, this is now where we could enter this one as the calculator. You're right. Because now we've turned it into a standard normal distribution. But I'm not going to do that yet. So I want to make sure we understand the tables. So if we look at doing this one with what we've got, we're wanting the area between these two things. So we've got the negative, here's a different color, the negative 1.79, and we've got the positive 3.93. And I'm wanting the area between these. So what will I end up doing with these two areas? Subtracting. So you're going to take the area that's to the left of the 3.93 minus the area that's to the left of the negative 1.79. So when we look at putting the 3.93 in as our z-score, so we're doing the 3.93. If you have the 3.50 and above, it's very unlikely that's going to happen just by chance. So we're getting that 0.99999 is what you're going to put in for those. So anytime you get an area, a z-score above 3.50, you're just going to use the 0.9999. And then when we do the negative 1.79, the negative 1.79 is giving me the 0.0367. So when we take that 0.999 minus the 0.0367, you should be getting the 0.9632. Well, now I'm looking at the areas. So I was taking the z-scores to be able to get my area to the left is the point, or the area between is the 0.9632. So my probability that a man is going to be between 64 inches and 80 inches tall is 96.32%. So 96%, a little over 96% of the men fall between 64 inches and 80 inches tall. So now the next part of the question is there very many people denied whatever we were in? The Marine Corps? Are there very many men denied being in the Marine Corps because of their height? Okay, so is that very many? Not really. So, yeah. So since there's roughly 4% of the men can't get in there, that's not that big. Now that's kind of significant. So there's still a lot of men that are ineligible, but it's not huge amount that are not eligible because of it. So most men can still get in even though they've got that height requirement. Questions on that one? 64 inches, that's 5'4". 64 inches is 5'4". 60 inches is 5 foot. So, well, that's 0.3 of a decimal, so it's 0.3 of 12 inches, so it's 4 inches. So 1/3 of 12 inches. Your decimals are not equivalent to inches. Okay, let's look at another example. If we look at number 22 on page 273. If we look at number 22, the Gulfstream 100 is an executive jet that seats 6, and it has a doorway height of 51.6 inches. First of all, what % of adult men can fit through the door without bending? Bless you. So we're still talking about men, so we're still using the mean of 69 inches, and we're still using the standard deviation of 2.8 inches. I want to know what % of men can fit through the door without bending. So what am I really looking for? Oh, yes, I am, without bending. So I want that probability that a man's height is less than the 51.6 inches. First of all, convert that to a z-score. No. Convert to a z-score. Because that would only work if that 51.6 was my z-score. And it's not my z-score, that's my x value. I haven't got a standard normal distribution. I don't have a mean of 0 and a standard deviation of 1, so I can't use what we've done yet. Oh, that's a 9, 69, and do it the other way. Do the 51.6 minus the 69. So I've got seeing everybody getting that negative 6.21 now. So if I want the probability that z is less than negative 6.21, What's it tell us from the tables? What was that? Yes, you were right. I'm sorry. Hillary was starting first. Okay, it's not 0.0001 because this is saying less than that negative 6.21. So since we're looking at the negative, we're looking at the area to the left still, and the negative 3.5 and lower is a 0.0001. So we can't say it's impossible, but we can say it's pretty close to impossible when we're looking at having those kind of values. So the probability that you're going to have a man that can just walk right through that door is less than 1/100%. So that's the first part of the question. If we look at part B, what percentage of adult women can fit through the doors without bending? For women, am I going to still use the same mean and standard deviation? No, because women don't have the same mean and standard deviation. The mean height for a woman is 63.6 inches. And the mean standard, or the standard deviation for women is 2.5 inches. Oops, wrong question. So we're still wanting to see if a woman can fit through that door that's 51.6 inches tall. So you're going to do the 51.6 minus the 63.6, take that answer divided by 2.5, and you should be getting that your z-score then would be less than negative 4.8. You should, yes. Because this was taking my original x values, my original scores when we had the mean and standard deviation from the population. This is now converting it into a standard normal z-scores. So once I know it's a z-score, now I can use my tables, and I'm trying to find the probabilities of those. And so now, what's the probability that z is less than negative 4.8? Still that same 0.0001. Chances of finding a woman that can just walk right through that door without having to bend over is also very slim. So then if we look at part B or part C, does the door design with a height of 51.6 inches appear to be adequate? Well then why didn't the engineers design a bigger door? What do you mean by safety during flight? I don't think that's really the reason, because most of your jets and stuff, you can walk through the door without having to bend over. Why do you think the jet stream would do it this way? Well, there is room for, it can seat 6. The Gulfstream 100 is an executive jet that seats 6 that has the doorway height at 51.6 inches. If they made the door bigger, what else is going to have to happen? You have to make the whole thing bigger. If you make the whole thing bigger, what have you just done? Made it heavier. You're going to cost a lot more for fuel, so the fuel efficiency has gone down. So in other words, what they've decided is to make it so it's a little cheaper to make and a little cheaper to run. We're going to make people bend over as they come in, and they can just deal with it. So they just made it to where the way they engineered it was making it just a design-wise, the 51.6 inches is just what they had to come up with, and they decided everybody can just say, watch your head as you get in. And it's short enough, obviously, that everybody is going to be watching their head as they get in, that you're not going to be coming up to it thinking it's going to be okay and then just bonking you in the forehead, because it's a pretty obvious it's short. Because we're talking a door that's, what, 4 foot, 3.5 inches tall? So, I mean, it's short. There's a lot of kids that can't walk right through it. Just the Gulfstream. The Gulfstream 100, just that style of plane. So that style of airplane has got a very short door. It's probably one of those that you walk out on the wing, would be my guess, and as you get in. It's not a very big airplane, but it can seat 6 people. Now, this is what Hillary's been really wanting to see. How can she avoid having to write everything into the calculator and or everything in there and doing it all by hand? How can we use the calculator? We've already looked at, and she was jumping to the fact that once you get it converted to a z-score, once you knew the z-score, we already figured out how the calculator could do it. You can also let the calculator just do the whole entire conversion for us. And so what you will end up doing, and again, it does have that limitation that it always gives the area between two boundaries. So if you don't have a leftmost or a rightmost value, you just pick something super extreme that would not just randomly happen by chance. So you just want to make sure you go very extreme when you do those. So what you'll put in is that same normal CDF. That's the exact same thing we did earlier. You'll put in your leftmost value, your rightmost value, and then you put in the mean and the standard deviation. So as long as you put all of those in, you're going to get your probabilities. So if I was looking at the that last question that we just did, where we wanted to figure out, let's go for men, the probability that a man has a height that is less than 51.6 inches, we would go into the normal distribution, second in vars to do the distribution. Do number 2, your normal cumulative distribution, and you're going to put in your leftmost value. Well, the shortest a man can be is 0, but we want to go extreme because the calculator or the statistics don't recognize that it has to stop at 0 because there are some things that can have negative values. So go with negative 9,999. That's extremely short for a man. Then you're going to pick that height that we have, which was the tallest was looking for the 51.6. Go with the mean. The mean for a man was the 69 inches. And then the standard deviation for a man, which was the 2.8. And it actually gives us the area as being the 2.586 times 10 to the negative 10th. When you see the little e's, that's telling me it's in scientific notation, which is telling me if I was to actually write that number out as far as the, we have the 2.59 times 10 to the negative 10th, you got to move your decimal 10 places to the left. That's the probability that you're going to get a man that can just walk right through that door. So when we're doing this in the tables are just going to give you the smallest value is always the 0.0001. A lot of times if it's extremely farther out than that 3.5, that's telling you it's going to be even smaller than that. That the probability was even less than that value, which this is giving, the calculator gives you a little bit more specific as what it is. I would write it as a 2.59 times 10 to the negative 10th. Makes a lot more sense. The book will tell you it's just the probability is less than 0.0001 is the way it'll show it a lot of times. Questions on that one? What's the wrong thing? The first number is your leftmost value. Your second number is your rightmost value, and those are the numbers you're given for just your x's. So if we went down to number 20, back to 26, when we talked about the Marines, when I wanted to know what's the probability that a Marine or a man is between 64 inches and 80 inches. So if I was putting that one in, I would go through and do my second in vars, do number 2 for my cumulative distribution. The leftmost value is a man could be 64 inches and get into Marines. The rightmost is your 80 inches and get in the Marines. Your mean is still the 69, and your standard deviation is still the 2.8. And so that's giving me that probability is that same 96. Before we had 96.32 versus with the technology we're getting the 96.29% chance. And again, that's just one of those. Oh, I'm sorry, I didn't have it in the middle. That's one of those the book gives you both answers on. The book will give you the answer with technology, the answer with the tables first, and then it'll say technology beside it, and I'll give you the answer with technology. Since those have a little bit of rounding error on them, rounding differences on them. No. On the test, you'll need to just show which way you were coming about doing it. So if you use the calculator, just write. If you use the calculator, just write that you did normal CDF and just write those and then write your answer so I know what you did. Versus if you use the table, you'll be showing a little bit of work because you convert it to the z-score and you'd show what those numbers are that you're subtracting. Okay, if I wanted to go the other way, if I knew my areas and I wanted to find my z-scores, well, we're going to do the same kind of concept as we talked about with the standard normal distribution. We just have to do that transformation in here. Start off, sketch a normal distribution curve, enter the given probability or percentage in the appropriate region of the graph, identify your x values that you're looking for, refer to the body of your table to find the closest area and find the corresponding z-score. Once you know your z-score, then you're going to use that transformation to be able to find what that x value is. So you're going to know your mean, your standard deviation, and your z-score, and then you're going to calculate out what your x value is. So you're using that same transformation that we knew, z is equal to x minus the mean divided by the standard deviation. You're going to have to do some algebra. It's such minimal algebra, it's amazing, that you're just going to have to multiply by the standard deviation, add your mean, and then you'll find your x value. So you got to do a little bit of algebra. You should know that if z is located to the left of the mean, you should have a negative number when you come out with your answer for your z-score. But then as you solve it, you may or may not get a negative number for your x. Refer to the sketch of the curve to verify that your solution makes sense in the context of the graph and the context of the problem. If you have a mean of, I just forgot what the number was for the heights of men. If you have a mean height of men is 69 inches and you know that you're looking for something that's to the right of that, and you get a height that's smaller than 69 inches, then that tells you you've done something wrong. You know the mean is 69. Anything that's greater, any probability that's greater than 50%, you're going to get a number bigger than 69. So that's what we're talking about with just make sure it makes some common sense as you're doing these kind of problems. So let's look at a couple examples. Let's do part D on number 22. This is going back to our Gulf Stream problem. So on part D, it's asking what doorway height would allow 60% of the men to fit without bending. Well, if I'm wanting to figure out what height is going to give me 60%, I know I'm using that, the z is equaling x minus the mean over the standard deviation. I know the mean height of men is still the 69 inches, and the standard deviation of men is the 2.8 inches. Will I expect, if it's 60%, is it on the left or the right of the mean? Okay, it's on the right because 60% is more than 50%. It's not a long way over here on the right, but it's over here. So I'm wanting this to be 60%. If that's 60% on the left, what is the z-score that gives me 60% on the left? So this is where you're looking in the body of your table for your 60%. So within my body of my table, I'm looking for my 60%. So we got the 0.5948, so we're getting closer. Right here, we got the 0.6026. Which one of those is closer to 60%? Well, if we take that 0.6 minus the 0.5987, we get 0.0313. Well, if we take 0.6 minus, or 0.6026 minus the 0.6, we're going to get 0.0026. So this one's closer. So we're going to use the 0.26. Is everybody okay? So my z-score is the 0.26. So my graph is off a little bit. But we are getting a positive z-score, which is what we knew we should. Now, what we have to do is plug it in. We're going to put our 0.26 in for our z-score. I want to know x. I want to know what height gives me that 60% of the men can walk through without bending over, minus my mean, which was the 69, divided by my standard deviation of 2.8. And like I said, this is where you get to do a little bit of algebra. To solve this for x, we're going to multiply both sides by the 2.8. To solve it for x, we're going to add the 69 to both sides. And so this is telling me that a man that is 69.728 inches or 69.728 inches tall is going to be able to walk through without having to bend over. We'll skip that one because I want to show you how to use the calculator. Calculator then, inverse normal was working with your standard normal distribution. Inverse normal works also whenever you're converting it and you have it in where the mean is not 0 or the standard deviation is not 1. Similar kind of thing. You're going to use that same inverse normal, which came from the second distribution, and then you did that, what was it, the third or fourth one down? Third one down. Going to do your area to the left, and make sure it is always the area to the left. So in this case, that's that 0.6. The mean, which was the 69. The standard deviation, which was the 2.8. And it's going to give you that same score, that x value that we had before. So you're putting in your area first, your mean, your standard deviation. It's going to give you a little bit of a different rounding error or rounding value because it's going to keep things a little more exact. We had to round to which z-score we were using, and we had to kind of go with whichever was closer. So it gives you the better value as you do these. All right, so we didn't get started on that last in section 4 at all. Currently, I'm still going to stick with October 9th. We'll reevaluate whether we'll be able to test next Thursday or not on Tuesday. This is the same assignment. I knew I wasn't going to get done with section 4 today, so I didn't even plan on assigning any of section 4 today. Section 4 only has 3 questions on its homework assignment, though. Section 4 is a lot of just understanding the basics behind stuff, so read those sections very closely, have a good understanding of what's going on, and then but do these. So always read ahead. So those are sections 4 and 5 that I wanted you to read right there. So have a good weekend.